Hello everyone. In this video, we will be talking about thermal expansion. When we heat things up or cool them down, they change size. They increase or decrease in length or volume. This phenomenon is what we call thermal expansion. When we're considering thermal expansion, we consider them in two different ways. We consider a linear thermal expansion. When we're talking about linear, we're talking about a change in length. So, for example, if we have a rod of steel and we increase the temperature, it will increase in length. Similarly, if we decrease the temperature, it will decrease in length. This is linear expansion. Then there's volumetric thermal expansion, where we look at our objects in 3 dimensions. When there's an increase or decrease in temperature, the volume of the object also increases or decreases. For example, if we heat up that rod of steel, it'll also increase in volume. If we decrease the temperature, the volume of the cylinder will decrease. We can calculate the change in length due to linear expansion using this equation. The change in length is the product of alpha times the initial length of the object times the change in temperature. Alpha is a constant. It is called the coefficient of linear expansion. This is specific to the material that you're using. For example, steel versus iron versus concrete. They all have different coefficients of expansion. Similarly, we can find the change in volume using this equation. The change in volume is the product of beta times the initial volume times the change in temperature. Beta is the coefficient of volumetric expansion. This is also specific to the particular material we're using. Let's look at an example of linear expansion. In this example, let's consider a steel bed. The steel beds are 100 meters long. Steel has a coefficient of linear expansion of 12 times 10 to the negative 6 at 20 degrees Celsius. The temperature in this region ranges around negative 30 degrees to 50 degrees Celsius. We want to know the space we must leave between adjacent steel beds to avoid any clashes or breaking of the steel. So, we must consider how much the steel can expand and contract based on this temperature range to know how much space we should account for between the joints. Since we're considering a change in length, we will consider linear expansion. So the change in length is alpha times the initial length times the change in temperature. Now, remember that this is in reference to 20 degrees Celsius for alpha. So we're referencing from 20 degrees Celsius to an increase in temperature or decrease in temperature. Let's first see how long the steel bed can get. So when the temperature increases to 50 degrees, the change in length is 12 times 10 to the negative 6 times our initial length of 100 meters times the change in temperature. Remember, change is final minus initial. Our final temperature is 50 degrees Celsius, and our initial temperature is 20 degrees Celsius. So when we find this change in length, we'll get it as 3.6 times 10 to the negative 2 meters. This can be the expansion the steel bed can experience when things heat up. Let's look at the lower bound, when the steel contracts. So the change in length is again alpha times the initial length times the change in temperature. Alpha remains the same, 12 times 10 to the negative 6 times the initial length, which is also the same. But now we're considering the steel contracting. So we're looking at the lower range. So the final temperature is negative 30 degrees from an initial temperature of 20 degrees. So we get the steel can contract by 6 times 10 to the negative 2 meters. And we denote the contraction by negative 6. So this can be the overall change in the length of the steel. So let's see totally how much the steel's range can change. So we'll consider that as D, which will be the sum of these changes. So 6 times 10 to the negative 2 plus 3.6 times 10 to the negative 2, which gives us the total range of change as 9.6 times 10 to the negative 2 meters, is how much space we must account for between the joints of the steel beds. When we're considering volumetric expansion or contraction, we're using the same methodology when we're solving the problems. All we've changed is the equation and the fact that we use volume and beta in these equations. Thank you for watching, and see you for the next video. I hope you found this video really helpful. The concepts and information presented in these videos will be true no matter what physics class you are taking. However, the concepts presented in this video are referencing material currently covered in Baylor University's coursework. Remember, if you're a currently enrolled Baylor student, we offer free tutoring services. Our tutoring center is located on the first floor of the Sid Richardson building. You will find all the details you need about these services on our website at www.baylor.edu/tutoring. You may schedule a free 30-minute one-on-one tutoring session online, or just drop in during any of our open business hours. For more information about our current services, please visit our website. Thank you.